So we continue with the gravitation, the remaining half of the questions. So let's start the 8A part 1, 8A part 2. This one is actually after you have done the first half of gravitation, right? You should have known, okay, what you need to put inside, okay? So just for the benefit of those who weren't here earlier, so see 3 points for the, maybe we look at gravitation potential first. So right, is the work done by external force, and you must have the per unit mass. And I stress, right, that you must say per unit mass versus, right, on a unit mass. This one is wrong, because, right, work done on a unit mass is still a joule, is an energy term. Only when it's work done per unit mass, right, that it become a joule per kg. Yeah. Okay. Then, right, from infinity to that point, obviously this one is also important. Yeah. So basically, right, we will usually mark until like that only. Especially if it's 1 mark, right? So without changing KE, usually we wouldn't mark. But if it's 2 mark, then it will be different. And then again, right, this definition, right, different teachers have different expectation of how much you need to have. So my advice, right, is all for definition, just don't err from the lecture notes version. Or as long as you write the lecture notes version, right, you confirm correct. Okay. Then next part, right, this one, why gravitational potential are negative. So if you recall, right, the gravitational potential, right, at infinity minus that at whichever point, right, will be equals to the work done, right? Okay. And we can rewrite this as this potential at whatever point is hence equals to the potential at infinity. Oh, sorry, it's divided by mass. Okay. Minus work done per unit mass. Did I get it right? Oh, wrong. The other way around. Okay. Because, right, it's from infinity to that point, right? So you start from that infinity, so that's your initial. Okay. So it is like that. With a minus and a plus. So we know, right, that by default we want the potential at infinity to be 0. Okay. And what are the work done per unit mass? This work done, right, is the work done by the external force, right? Since the external force is always acting opposite to the gravitational force and opposite to the direction that you're moving the mass. Just in case, right, this one you also not too clear, I'll just draw it out briefly. So this is at infinity, and the mass is like on the way coming in, right? So let's look at the forces acting on it. The Fg, right, depends on the distance lah. Okay, so it's like getting bigger as you come further in, and but that's not the important point. Important point, right, is where's your F external. F external, right, is always to act opposite way, because you don't want to increase in Ke ma. So you don't want this to accelerate. So this is your F external. So you're always moving inwards, whereas, right, your F external is always pushing outwards. Hence, right, the work done will be a negative work. Okay. So this term, right, is negative. So overall, right, you see this potential at the point will hence be a negative value. So that's what the words here are trying to convey. Okay, the words here are trying to convey. Gravitational potential is gravitational force is attractive. That's why your external force needs to be outwards. Okay, and that will make it opposite direction to the displacement. At infinity is taken to be 0. So all this together, right, will allow us to conclude why, right, the phi here always negative. Okay. If you are unsure, right, this part of the explanation, you play back one more time to go and listen. Next up, right, we have the variation of potential against R for Jupiter. Okay, so from this graph, right, we can actually deduce, right, where's the Jupiter's radius, which is somewhere here. This is Jupiter's radius. But actually, in a real life, right, Jupiter is very hard to define radius, because Jupiter is a gaseous planet, if you know. There's a few planets which are gaseous, a few planets which are solid. All the planets near Sun are all solid. All the planets after Mars, right, are all gaseous, or it's a cloud of gas. There's no rock. Okay, so if anyone asks, like, why don't people go and find do exploration on Jupiter, or this, right, to colonize there, settle down there? Nothing for you to settle, or you stand there, you sink into the gas. Okay, so Mars is the furthest planet that you have like rocky surface. Yeah. So anyway, back to this, right? The phi against R. So you see this question, right? You by now you should have guessed R. So this one definitely must draw gradient, draw tangent, find gradient. Okay, that kind of one. So it's highly predictable already. And that's the first part. Okay, so we draw a tangent to the 4.2. I have drawn this tangent. I will not show you how I draw it, or you can go and try. How do you know that your tangent is correct, right? If your value is close to mine, okay, whatever I show you here, right, then you're correct. Okay. And we usually allow a range. This range is not written in a suggested solution. My guess, right, is that this range is around 0.72 to 0.76 will allow. Okay. This is 0.74. My answer is 0.74. So 0.72 to 0.76 all correct. If this has more marks, then we will deduct accordingly. If you veer from this range, if you quite not too far, still okay. This question, right, also I'm not sure the marker will be how near, okay, but if you notice, right, there is a 10 to the power of 8 on top, 10 to the power of 8 below. It turns out, right, these two cancel out perfectly. So there's no way that you can make a power of 10 error, even if you forgot to realize, right, there's actually a power of 10 in the axis. Okay. Once again, right, whether a marker will deduct you a mark, right, based on this, right, if you actually never write it in the working, because your answer confirm will be correct. But if your working don't have, right, marker may deduct a mark. Okay. So so actually, right, a lot of things you need to be quite careful one. And it's not difficult once you are aware of it. Okay, once you build awareness one time, after that, right, you almost wouldn't 踩地雷, or you're always correct. Here, right, I wrote how to understand direction from G equals to minus d phi dr. Okay, so let me just go through this, right, quite quickly. You see, this is the planet. Okay, so this is Jupiter. And this is the R, okay? Yeah. So R, right, is like pointing outwards, right now. So this R, right, the arrow direction means that outwards is positive. That's what it means. Okay. And it doesn't exclude, right, the other side. If you go outwards in the other side, also positive. It simply means outwards, because this R also never define which direction, but it simply means outwards. Okay. And you know, right, G actually in the definition, right, is equals to minus d phi dr. So you look at this graph, right, the potential is like curve upwards, right? So any tangent that you draw, or whether you draw it here or you draw it here, you notice, right, the tangents, all these are all positive gradient. This positive gradient, right, will mean that this is a positive d phi dr. I shouldn't write it as plus sign. I should just write as it's a positive d phi dr. And this must mean, right, that it is a G will be negative. Okay. So what does it mean? it means, right, the G around Jupiter is always pointing inwards. Oh, which makes sense, yeah, because gravity is attractive, yeah. And that's how you, I mean, you don't need this information to predict the second part, which is why is it the direction is towards Jupiter, okay? I pause here. Any question thus far? Or feel free to interrupt me anytime you want to clarify something or check whether your answer, however you phrase it, correct, acceptable or not. So next up, find the GPE of the moon. This part is also very straightforward. So you already know the position of the moon is the 4.2. So you read off the y-axis. So this one is read off from graph. Okay, so check your answer. But if you see, if you have made the power of 10 mistake, right, you didn't read off the power of 10, then the power of 8, right, this part, you confirm deduct mark already, yeah. Then next up, right, now you are told that if you project a rock, right, from the moon towards Jupiter, okay, then the GPE will look like the one given, and how will the total energy and KE look like, okay. Let's start off with talking about the KE first, okay. 1 point. Because this question says, right, that you are trying to launch the rock with minimum speed to reach Jupiter. Means what? If we recall from the last lesson, right, whenever we look at this kind of curve, right, or potential curve, right, this is a term that I coined, this is a potential landscape. It's like a landscaping. So here you have a hill, okay. The hill, right, is like asymmetrical hill. There's a peak. The peak, right, is nearer one side. So how do you get something, right, to go from one side of the hill to the other side? You just need enough energy, right, to give it a kick up to the top, okay. Then after that, you will roll down already because the other side is downslope, downwards. So if you think about it as a ball, you roll a ball enough with enough speed up to the peak, then it will roll down by itself. That's exactly what is happening, okay. So just enough speed, right, means the KE at the top, right, first point that you will know, it will be this point, okay. So this is the first thing. Then after that, right, you will know the second thing, which is hence, right, total energy. Because at this point, right, this value is 0 for KE, then you plus the GPE, right? So the total energy, right, will be as such. So this is the second thing. Then finally, right, so once you know the total energy at one point, right, then it will just be constant. It will just be constant. Then, right, you can go on and complete the curve, or the mirror image of GPE will be a KE. But key thing, right, is actually this one don't have values. If got values, right, you actually need to be quite careful. Okay. Is there? Don't have them. Don't have. Yeah. There's no need for values. I could have made this graph, right, this question difficult by just calling, right, the rock to be 1 kg, and I ask you to draw energy, and you therefore, right, may need to also cannot. No way, we are not given any numbers. Forget what I say. Yeah. So what I want to say here? Which is how we know, right? This graph draw until how high? Mirror image is mirror image, but right, you got to realize what's the mathematical relationship. You see, this height, right, is a negative number, the GPE negative. Then this part is KE, which is positive. So together, right, they must add up, sum. the sum, right, will end up equals to this value. Okay. The sum must give you this value. So this part of the graph, right, has to be slightly less positive than the GPE is negative. Yeah.
Mr. Quet,
Yeah.
how come the total energy is constant?
Anyone disturb the rock as it was flying from the moon to Jupiter or not?
No.
So total energy is constant.
Oh.
When do you know total energy is not constant? The only reason why it will not be constant, right, is for this gravitation question, it may be a satellite in the orbit, it may be a rock flying from infinity inwards, a rock flying from moon to earth or whatever. As long as it's flying out of its own will, right, there's no work done on it, then total energy will be constant. If there is, like, for example, the rocket fire is thruster, okay, then right, it gains speed, then you know total energy is not constant anymore. Then you need to make sense accordingly. Or you're told, right, there is resistive force, then total energy will decrease. Okay, so only when there's an interference of some other forces, right, then total energy will not be constant. Okay.
Okay, thank you. Also, how come the total energy is at the turning point of the GPE curve?
Add up the number, lor, because at this point, right, the KE must be 0. Or why must it be 0? Because that is the context of the question. It says, right, the rock is projected with just nice, right, the minimum speed in order that it can reach Jupiter. So how much speed must it have? It must have enough, right, so that it can roll up the potential slope from the moon side where it's launched. Also, you look from here, right, there's a tiny slope here. So this rock, right, must be able to climb this potential slope. I use the word climb, right, it's like to make it figurative. That's exactly what the rock is feeling like. It feels like it's climbing a slope. It will convert its KE to GPE. And how do we get to the top? It will get to the top, right, just nice, or it use up all its KE, convert into GPE already. Okay, so its KE at this point will be 0. So that's why I say the KE, right, we know the value at the top is 0. That's the first thing we will conclude. Then you deduce next, right, total energy will be sum of KE and GPE, so you plus these two values together, lor. So you'll be, because KE 0, so total energy at that point will just be the GPE. And total energy will be the same across all points because nobody disturb it. 明白吗?
Okay, thank you.
Okay, very good. I'll clarify whenever you are unsure. Make sure, right, that you walk away almost 100% clear. Okay, if I let you walk away and have more doubt than you come, right, then my teaching fail already. My job is to make you understand. Okay, let's go on to the next question. Blah blah blah. You have a satellite geostationary around Earth. Whatever. Okay, a lot of story there. So 3 conditions for satellite to be met. This one is bookwork, same orbital period, same direction, and same must lie on equatorial plane. Okay. At this point, right, I want to add on to what I didn't say the last time. So geostationary orbit, right? I hope you can imagine. This one is a 3D drawing. Geostationary orbit, right, would be something like this. Of course, it's not drawn to scale because it's supposed to be around 7 times Earth's radius. Okay, so this is fine. If you see, right, the orbit, right, is like this. Okay, at an angle. then you should be able to see, right, why when the Earth turns, the satellite, right, will always be at different part of the sky. Okay. For example, when you are here, right, at this point in time, the satellite could be just above your sky, right? But later on, when you are here, the satellite, right, will have moved to the northern part. Sorry, you can see. Okay. So later on, right, when this one turn, okay, satellite move. I mean, actually, you are talking about the same point. I shouldn't draw a second dot on the Earth. A while later, right, you see, at this moment, you see, let's say the satellite is above the sky or at the equator, fine. A while later, right, this satellite will move into the northern hemisphere. So relative to the person in the equator, right, you see the satellite move to one side of the sky. Then you move further and further in the northern hemisphere, right? Then you see it move, right, further and further to one side of the sky. Then after that, it move back. Then half a day later, you may see it directly above the same point of the sky. If you can actually see a satellite, or recall, satellite, geostationary satellite, by right, is supposed to be always in the sky. I shouldn't say by right, it is, okay? It's just daytime, you can't see it. Or once nighttime, you automatically see it. Then the second half of the day, right, the satellite will appear on the other side of the sky. So that is why, right, this one is not geostationary. You may still see it, but right, you may not, you wouldn't see it at the same part of the sky. That's a thing. Or in case, right, you're not very persuaded by why is it not geostationary. Okay. Furthermore, right, let me ask you, this is not about geostationary, but satellite in general. Suppose, right, I have this orbit. Okay. Can happen or not? Can this orbit, right, that I drawn materialize?
Cannot.
Why?
Because there's no force to provide for centripetal force.
No force to provide for centripetal force. Quite right, quite right. Okay. Yeah, so it's actually right. If you are talking about this orbit and you draw the satellite, right, the gravitational force, right, will be pointing towards Earth, what? But you actually need the centripetal force, right, to provide for, you actually need gravitational force to provide for centripetal force. And the centripetal force, right, needs to be in this direction one, or not? So it means, right, gravitational force cannot provide entirely for centripetal force. And there needs to be, like, you need to fire a rocket somehow, or such that the net force, right, is towards the center. And this doesn't make sense, because of the satellites are supposed to be freely orbiting one. You don't need to fire create any additional force to force it to be like in orbit. Yeah. So that is why, right, this thing confirmed cannot on. And sometimes the question may ask, why cannot? So you'll say, right, because gravitational force, right, cannot provide for the centripetal force. In this case, additional force is needed. So this is not an acceptable satellite. Okay, so we don't talk about the 3 points so much. It's good work. Let's go on. Okay, this part, right, you are given you see, you are given informations, right, in not a very straightforward way. You are told, right, number one, the G at the surface, or G at surface, is this number 8.6. Yeah. Actually, I find this thing is very fun. This thing is very funny. No need to have this one now. Okay. As long as it's spherical and it's uniform, then fine already. So in case you're confused by this thing, right, you can just ignore it. It's just trying to tell you, right, whatever this is trying to say, mass concentrated at the center, it's just trying to tell you you can use the formula without worry. Okay. Then you're supposed to find, right, what is the altitude of a point A and you're also given further information about the potential at that point. So you see, to find the potential, right, is either you have Gm over the R, right, or at that height is equals to 5.2 times 10 to the power of 7. But right, you don't know what is the G, or this is a question mark. Okay, so in the back of your head, right, you're thinking, hey, how do I get the M? So one way, right, is to realize that you have information about G at the surface, and you also have information about radius of the planet. Okay. So with that, right, then you can write out what is the G at the surface already, is equal to Gm over radius of planet R square, okay, equal 8.6. So we actually don't want to evaluate the number. Don't go and find M, yeah, because you find M later on, you still need to times back the big G. So just leave it. Oh, then here, right, and furthermore, question didn't ask for R. This R, right, is actually capital R plus the H. And usually, right, capital R, we reserve it for radius, okay? Most of the time, but sometimes the question may just use R for separation in general, or big R. Or small r is separation in general. Big R is usually a fixed radius or a certain known radius. Okay, so with that, right, you can do your substitution. So Gm over big R plus H. So I straight away use this already because I don't want to write out the small r, then later on still need to minus. I just write out this. Just later on I may forget to minus. So, so yeah, so this is how I will present. Okay. Okay or not, this one? So the next part, right, what's happening is a rocks, right, falls from rest. Yeah, how to fall from rest one? This kind of wording is no good, but then it's just trying to tell you, right, a rock came from far away, okay? And it come towards this planet, okay? But you pass by point A, yeah? So at the point that it passed by point A, what is the speed? So we are considering, right, these 2 points and apply conservation of energy. Okay, so conservation of energy, we always need to have 2 reference point or 2 reference state. Okay, then you compare the KE and the potential energy. Okay, so you obviously, right, the rock will gain KE and lose GPE, and the calculation is actually straightforward. So finally, we have the rock speed to be 1.02 times 10 to the power of 4. And once again, I want to remind you, always write this part. Don't write out half mv squared equals to something. This is actually a loss or gain in something. It's with reference to another quantity. So it is because, right, it falls from rest. So the initial K is 0. So don't write without the minus 0. Always write the minus 0. Move on. Then the next part is, this is still straightforward. They ask you, right, another point B above the surface, the potential is minus 6.8. Okay. So we see, right, the potential for point A is minus 5.2. It's minus 5.2. Then where do you find point B? Minus 6.8. So if you actually draw the graph, right, the graph of phi against R will be like that, long. So more negative means is nearer. So this must be point B. or compared to the phi of A, which is like less negative. Understand? So point B must be somewhere here. Oh, that means, right, the rock will have fallen a greater distance, and lost more GPE. Thus, you will have greater KE by the time you pass by point D and greater speed. Okay, so I think this logic, right, most people can get it quite well if you have understood where is point B. Pause for a while. Any question?
Mr. Quay, just to clarify the above part for the gain in KE equals to loss in GPE, that part, right? So the
Yeah.
gain in E, you're taking final KE minus initial KE. Then why for the loss in GPE, you take like initial GPE?
Minus final.
Yeah.
Correct. Okay, good question. You see, why I choose to write this version? Actually, we can. This one will entail, right, the 3 version of writing conservation of energy statement. This is the verbatim form of means what is, right, saying we account for energy changes, right, either by mathematics purely, or we use words, right, to help us convey the accounting. So we say gain in something, loss in something. When we say gain in something, we obviously know that this gain is a positive quantity, right or not? Okay. But when we say loss in something, right, is this a positive quantity or is it a negative quantity?
Positive.
Still positive, right? Because we will have account for the is it positive or negative, right, by the word loss, and account for it, right, by putting it at the correct side of the equation. Thus, right, if you are saying there's something lost in something, means at first you have more, later you have less. And what I'm trying to do is to find out what is the size of this change, or the this drop, right, is how much. So I'll take a big number minus a small number. Okay. So whether we are talking about gain or we are talking about loss, right, when we come out with the who minus who, is always large minus small. Okay. So if you gain, means final minus initial. If you lost, means initial minus final. 明白吗?
Yes, okay, thank you.
Actually, I like this kind of question, because this kind of question, right, are always things that people have on their mind, seems to know, but not too clear. Rather than, you see, all these things are very important to clarify. More important than clarify how to do difficult question. Because difficult question come and go. Or to be good, right, at least to be proficient, like get an A consistently, that's my answer. How come all blank? Jialat. Aiyo, where's my answer? Oh, I was saying, right, it's more important to clarify basic things. Okay. Let me search for my answer. Aiyo, how come like that? I'm not sure whether is it in a separate file. This morning, I spent 2 sessions to do, right? Then the first session, I save first. Second session, I hope it's here. If it's not here, right, then die already. Aiyo, this one even worse. I hope this is the one. Oh, okay. No worry, everything is under control. Yep. So next question. Define gravitational field strength. This one also mentioned before. And just to be lost all, remember field strength is a force, or it's a per unit mass force. Yeah. So think about field strength, right? And not just gravitational field strength, but in general, this kind of quantity, right, is just like saying, right, fish, or let's say you're comparing prices of fish. This piece of salmon, you see, go to the market, this piece of salmon, $30. Another piece of another fish, maybe what's my favorite? Cod fish, or $40. Or $20. So salmon is 30, cod fish is 20. Can you say that salmon is confirmed more expensive? Yes, like in a certain sense, because it's bigger, absolutely. But then, right, you want to compare the quality of the absolute market rate, right? You don't just use the price. You'll say, right, oh, let's look at the price per kg of the fish. So this salmon could be 1 kg and it's $30, but the cod fish may be 20 kg and it's only half a $20, but it's half kg. Thus, right, the cod fish is actually $40 per kg. So cod fish is actually like more atas, right, or more expensive. So similarly, right, that's the idea why we use field strength and why we use potential. We want to quantify the property of that point, right, without considering what we put there. Yeah. And next, right, why must have a small mass? This one can be asked also. Okay, is right, so as not to distort the field. Okay, so if the mass is big, right, the mass that you put there also have its own gravitational field contribution. So whatever that it end up experiencing may not be the real field at that point already. Okay. Next part, this part is actually not a difficult one. You see this common in the MCQ. So you are given, right, this particular asteroid. Oh, pay attention, this is an asteroid, because later on, right, the rest of the parts will make sense. You're given a density, diameter, so you go on and calculate the G. So this is not too difficult. Except I want to remind you, right, to simplify until here, or keep on simplifying until cannot simplify, then substitute. Okay, and in this case, right, the indices, no, what am I saying? Coefficient times coefficient, power times power, right, will come in very handy because all are multiplied. Also is very neat. Okay. Next up, right, we are going to deploy a space rover. It's just a mini car or those kind of remote control car like that, to drive along the equator of the asteroid. Yeah. You see, that's why, right, you can actually go around the asteroid. It's not too big, or you can't go around a planet. Yeah. And anyway, so why is there a maximum speed, right, that a rover can drive without leaving contact? So we recall, right, why when the rover goes around the planet, right, it's actually performing circular motion. So this is actually a circular motion question. We look at from the top view. So this is the North Pole, right? So the car is like here. This is FG. Okay. And normally, right, we will expect there to be some form of normal contact force. Okay. Yeah. But if this car, right, is indeed going around the planet, right, in a circle, then we know there must be centripetal force. And hence, right, for the centripetal force to exist, Fg must be greater than N. Okay. And if you have the circular motion faster and faster and faster, whether you consider v squared over r or mr omega square, right? You can see if you go faster and faster and faster, right, means that your centripetal force need to be greater and greater and greater. Okay, to provide for this greater centripetal force, Fg wouldn't change because you are at the same distance from the center of the asteroid. N will become smaller, 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 smaller. Okay, so as V increase, right, or omega increase, R is constant, then N will decrease. Okay, and N can decrease until what? Decrease until 0. Oh, so that's what this whole thing is trying to say. The maximum centripetal acceleration, right, is given by the gravitational field strength. So that's where, right, A equals to G. And hence, right, there's a limit to how fast it can go. Okay. And one thing, right, if you are very clueless about all these things, whenever you see contact, you must think from the point of view of N. Okay. Anyway, I didn't write out the equation. Let me just write it out. So Fg minus N equals mv squared over r. Okay. So N must be greater than 0, right, for contact. Okay. So you will see, right, hence V. Okay, let's shift it. Sorry, let me write this again. Fg, right, minus N equals to mv squared upon r. Okay, so let's make N the subject first. So N is equals to mg minus mv squared upon r. So if this is supposed to, if you want it to remain in contact, right, so you want this N to be greater than 0. So end up, right, you will have V, or you do the inequality, right, must be smaller than Rg. Okay, so this is the upper limit. So the question could have, later on confirm will ask you to calculate this one off. So let's go on. Oh, no. This question is not to calculate the V, but to calculate the period. Okay, so but it's along the same vein. So you want to make N equal to 0. So at that point, right, AC will be equals to R omega. AC is R omega square and it's equals to G. So you solve for the T in terms of everything else, and you get this period. Okay, so once again, right, what's the significance of this? Is if the T, right, is greater than 7.52, then okay. If less than 7.52, fly off. So yeah, in fact, that's what we are supposed to do in the next part. So what will happen if you go too fast? You will, number one, lose contact. Lose contact, then do what? Because, right, you see, it still have a speed, if it doesn't go into circular motion, right, at this point, suddenly the speed, right, starts to exceed limit, right? So end up, right, the excess speed will cause it to just leave this circular motion path. Circular motion path is like this. You just leave off this path. So relative to the ground, this felt like a projectile motion. Okay. But actually, right, this one I'll have some reservation. If you don't think too much, it's fine. If you don't think too much, you will write out the answer that I show you. But I will have reservation because the asteroid is very small. So G at the surface, right, is still uniform, but G above the surface a little bit, right, may not be so uniform already. So, but we don't need to worry. This answer is perfect for an exam. And if you don't know what I'm talking about, right, in the past 30 seconds, don't worry at all. So you see, this is the projectile motion and land back at the planet. Okay. Any question? Go on. Explain what is meant by neutral point. Okay. This one definitely will have a lot of variety of answer. In the past few explain kind of question, right, for gravity, it's all standard one. Okay, there's no other way you can say about the condition for geostationary or why GP is negative, this kind. That one is quite standard. This one I think will have variation in the answer. People will write different things. This is one way. Okay, so you say gravitational field strength due to Earth is equal in magnitude and opposite in direction to that due to Moon. Okay, so what we are saying, right, is at the neutral point, which is like here, or nearer to Moon, this guy, there's a G due to Earth, and the other one also got a G due to Moon. Okay, and they are equal and opposite. So the resultant 0. G is a vector. So at this point, I want to hear your answer. Maybe you want to tell me, or you want to check whether your answer can or cannot. I'll tell you. Anyone?
Mr. Quek, what if I wrote the same thing, but instead of writing gravitational field, I wrote gravitational force?
Okay, if you write gravitational force on a test mass, also can.
Oh, okay.
Must have on a test mass, because cannot have don't have object to have a force. So see why when you talk about field, right, you can imagine the tug of war, right, being played out, right, without having something being there for you to pull. But when you say force, right, you must have someone there for you to pull. For example, right, you can compete with another girl, okay, then to see who more attractive. Or you all can compete, right, in the imagine sense. Or they say, my hair nicer, or the girl's eye nicer. But overall, 综合起来, whose attraction, how much can compare. Or if you want to say the actual attraction, you must ask a guy, hey, come, or you stand here, you like who more, then you must have an object of attraction to have the force. Any other version? I read out a few versions. You tell me whether correct or not. Let me find it. It's which question? Give me a minute. Let me find the correct page.
Mr. Quek, can I put there is a point where the gravitational field strength of Earth and the Moon cancels out?
What does it mean by cancel out?
0.
Okay. The thing is, right, you actually don't need to answer already. That question is rhetorical. The fact that someone can ask you that, right, means you die already. Because in exam, you are not going to be there to re-answer it. The marker will have a question in their head. And when you are marking, right, we cannot text you, excuse me, this student, what do you mean by cancel out? Then you reply, oh, I meant this. Oh, okay, got it. I'll give you the mark. Oh, so answer must be one time, okay? So what is problematic with that, right, is cancel out, right, give to 0. But why does it give to 0? Could it be two number, one is a positive 5, one is a negative 5, add together give you 0? That one is also cancel out, right? But that is a scalar cancelling out. Why not? Two scalar add together give you 0. To talk about neutral point, right, you need to make sure that the idea of the vector come across. So the direction also important. Yeah.
So I cannot.
Correct.
Even, even if I say if there is equal 0, also cannot.
Also cannot.
Okay.
Because how they cancel out, cannot feel the how they cancel out come about. Is it a number cancel out, or is it a direction, the vector cancel out vector? Yeah.
Okay.
Okay. Next up, want to clarify.
Can you say that the gravitational field strength is, wait, I mean the neutral point is a point where there's no net gravitational force on the object?
Cannot. This is according to the examiner comment. Let me read why they say cannot. They simply say, right, the comment here, it says, right, it's insufficient. You need to provide more detail of why it becomes 0.
Oh, okay.
So whether you say, right, net gravitational force acting on a small test mass is 0, or you say net gravitational field strength is 0, both also cannot. So even if you use the force method to say, right, you must say the force exerted by moon on the test mass equals to the force exerted by the earth on test mass but opposite in direction. You must say until like that. Show that it's vector cancel out vector. Okay. So see, which is why I draw this diagram, is to show you, right, this diagram is the physical picture of how you translate this diagram into words. Yeah, so that's the idea here. Okay, so we go on. The spacecraft go from Earth to moon, go from Earth to neutral point. Okay, what's the question about? I also forgot already. Okay. Question told you, right, the spacecraft need 6.1 times 10 to the power 10 joule to reach neutral point from Earth. Okay, so what is the potential at neutral point? We already know Earth's potential at the surface of Earth, and we also know mass of moon. So we construct out this one. Okay, so this is the in COE term, right, conservation of energy term. See, this is a work done, okay, by external agent, and this is the change in GPE. Okay, and you may ask, some people may think more, right, and ask, what about a change in KE? Need to consider or not? Okay, in this case, right, because of context, is no need. So this work, right, needed, right, is the minimum work. Means, right, we only move it without speeding it up. Or if you speed it up, right, means you need to do even more work already, ma. So this is implied in the that wording. Okay, it's purely, right, the work done by the external agent is like that. Just in case you are thinking why there's no need to consider certain thing. Okay. Otherwise, right, this, I think a lot of people will also get correct one, this one. Then, right, what about what's the minimum KE to send the rock from moon to Earth? Okay, so this one, right, is the same thing as what we talked about just now. So moon is here, Earth is here. Okay, so from the surface to surface, right, the graph is like that one. Okay. Task, right, to send from moon to Earth, all you need is to send moon to neutral point. Okay, send the rock from moon to neutral point, and then you consider the conservation of energy for this process. So in doing so, you lose KE, gain GPE, and then you just substitute in the newly found potential for the neutral point. You can solve. Okay. I pause for a while. Any question for this part? This diagram, right? Are you very clear? Why is it like that? Yes, no? Oh, if you're not clear, right, you can refer to your what, lecture note, okay, the appendix. Got one part, give the full it's not a derivation. I show you, right, how to go about understanding how to construct this potential between Earth and Moon, or it's just taking the sum of the respective potential against R graph, add together, give you this curve. Yeah. What is more interesting, right? Since it's a revision, I want to talk about the gradient. Just now I also say, right, what I want to say, G is equals to minus d phi dr, right or not? So applied to this, right, you see, gradient on this side is positive gradient. Okay, hence, right, negative G, which means what? G is to the left. Then on the other side, right, is negative gradient. Okay, means, right, positive G, which means to the right. Okay, and finally, right, why this point, the neutral point? What's the meaning from this graph? This is gradient equals to 0, so G equals to 0. Yeah, this is just revision. Some of you may find this boring, or you've heard this so many times already. Okay, let's go on. Next page. This part is not related to the earlier one already. So first up, expression for the gravitational force. This one, right, when I look at the suggested solution, I also find a bit strange. The suggested solution, right, wants this version, okay, but I actually think write out this version will be good enough, really. Okay, so in case, right, you think the same way as I think, and you only write out until the algebraic form, never substitute anything, you will be losing 1 mark by the mark scheme. But no worry lah, it's just 1 mark. So this physics exam, you'll just get 99. Not too bad lah. You should top the cohort if you get 99. Okay, then so we go on. Centripetal force is provided by the gravitational force, right? Whether is it talking about here, or this is the Fg, or it provides for centripetal force of both. Yeah, but what is the difference is, right, the right hand side is different. So this is m2r omega square, whereas this one is equals to 2m r omega square. See, our formula is mr omega square, right? So you see, they actually orbit about their common center of mass. The bigger one will have half the radius as the smaller one. So my mass 2 times, but my radius half time. The mass 1 time, but the radius 2 times. So it works out to be exactly the same. Okay. And for a binary star, right, it is necessary that the omega is the same. How do you know? You write out this equation, you can also know what, because Fg on in both equation must be the same. This is an action-reaction force, they come in a pair. So right-hand side, right, even if you don't know whether the omega are the same, you just write omega 1, omega 2. Since the other terms are the same, right, then it also means that omega 1 equals omega 2, or have to be the same one, because they cannot have different period, then they will not be like spinning about the center of mass anymore. You got to visualize that. Anyway,
Mr. Quek, you know the gravitation force of attraction part. Why is it not why is the denominator not 9r squared? Because like the distance between the stars is 3r. Then when you square 3r is 9r squared.
Oh yes.
Okay.
It's my mistake. I write wrongly.
Okay.
Okay. Yeah. The final answer is correct, because I copy from the suggested solution one. Numerical one is correct. Okay, then you go on and figure out what's the R law by solving it against either one. Whether you put M2R or 2MR or right hand side is the same. Yeah. So here is just solving. And once again, I want to remind you, always right, substitute it only after you make subject. Okay, very important. These are not physics. No, this is just like routines that will, good routine help you solve things fast and easy and accurate. Bad routine, right, will make you drop marks all the time. Okay, last part, the astronaut, blah blah blah. Okay, you see this phenomenon, right, whereby the astronaut appear to float inside the capsule. Oh, by the way, right, 4 humans who are not trained astronauts are floating in space right now. Do you know what's that about? Anyone?
Isn't it the SpaceX, the civilian launch thing?
Correct. So what's happening? You want to tell the rest who don't read news?
I just know it's like one very rich and then 3 other not so rich were able to launch into space, and then they're coming back in, I think, a month, or is it a few weeks?
No, 3 days. 3 days time.
3 days.
4 days total, I think, or 3 days total. I forgot already. Anyway, right, what are they doing? This is a very good business. Elon Musk, right, collect a few hundred million from the very rich guy who also invited a few random person to join him to test his rocket and make publicity. If rocket crash, right, then he, too bad, sorry, you sacrifice for science, and sacrifice for Elon Musk. Then at the same time, right, he get money. Okay, so see who will want to get, who will actually pay to be guinea pig to test out product, that rich man who paid 200-300 million to Elon Musk. By the way, right, just for your general knowledge, this SpaceX program, right, the Falcon rocket, what is special about it, right, is usually in a spacecraft, right, when they fire out, they have a few rocket booster. Okay, you can think about it, right, as a fuel can. Okay, contain the fuel, burn, launch you to a certain speed high enough, then you use finish the fuel already, right? Then you just throw away the can, because right, if you continue to carry the can further, right, then your second canister of fuel come into burn again, right? You still carry the first empty tank, which is like extra mass, so no good. So by right, once you burn finish one, you throw away the empty can, and then you continue to go the second leg, okay, burn the second can, and use finish, throw away again. So that's the traditional method. So what Elon Musk rocket are doing, right, is they managed to recycle the can. So the can will own self fly back, okay, and land on the sea. Then you go and recover it, okay. Hey, I don't know whether it fly back or just recover it back. There's a version that can own self fly back and land properly one. There's another version, right, is drop back into the sea and you recover it. But in both cases, right, you save costs because, right, that thing, right, is not, it's reusable, so you can use many times. Which is why, right, 200 million for this trip, right, is actually like the cheapest ever already for such a mission. Or usually this kind of mission is not cheap. Talk too much, okay? So go into this orbit, right? This phenomenon is called what? Appear to float. For the astronaut in the orbit, what is this phenomenon? Got two words.
Is it like apparent weightlessness?
Oh, you guessed the word before I even finish the hangman thingy. Okay, yes, apparent weightlessness. Yeah, so what happened, right, is you see, Earth is here, space capsule is here, man is here. So space capsule, right, has a certain AC, which is equals to, right, the G at that height. Man also have the same AC, which is also equals to the G at that height. That is what allowed them to go in circular orbit. Yeah. Thus, right, their centripetal acceleration is actually the same, which is the G at that height. Just that the centripetal force is not the same because centripetal force is mass times acceleration. So these two may have different mass. I mean, definitely different mass. So for statement B, right, the student B, that is the reason why, right, the statement B is wrong. They have same centripetal acceleration, not force. Then A is of course also force also because this guy actually has his own Fg. It's just his Fg is equals to MAC. And why do they appear to be like he is displaying weightless? So let me just elaborate, right, quickly on apparent weightlessness. This apparent weightlessness, right, manifests itself in many situations. As long as, right, person falls at same A as environment. Okay. For instance, right, you play those kind of 海盗船 also can, very hard. That one is harder. So suppose, right, you are in a lift or you are in a cage. Someone, right, cut the cable that's holding the cage. Both you and the cage will fall at the same rate. Then you can actually have a thrill, right, of feeling how it feels like to be an astronaut in a spacecraft, except, right, that he doesn't crash and you would. But anywhere in between, right, between falling and crashing, right, you'll feel like an astronaut in a in a capsule. Okay. A 5-second version of the $200 million thingy. Okay. Last question. Binary star again. This number, right, I'm very angry. Why Wachong question, right? I can put this kind of number. No star is 10 to the power 18 kg one. This one is like a trillion times lighter. Okay, star must be 10 to the power 30 and above one. Our sun is a very small star already, 10 to the power 30. Okay, and nothing to do with the question. Okay, so find the orbital speed of this thing. Okay, this is straightforward. So you do GMM over R square equals mv square over R. I shouldn't say it's straightforward because right, obviously there are people who got it wrong, and where do they get it wrong, right? Is this and this, okay? There's people who don't know the meaning of terms, right? They just substitute in things, right? They will mess this up. Or the right hand side, the radius. They will just think that right hand side mv squared over r is the normal r law. But here the r refers to radius. Okay. Whereas this r refers to separation or different meaning. Yeah. The calculation, nothing much to say lah. So, yep. Why GPE is as gravitational potential is negative. This one say before. We skip. GPE of the system. Okay. This is an interesting thing. I want you to pay attention to this. When people do this question, right, they will have a question mark in their head because got two mass. Why not? Here, right, you got the GMM over R. Then here also got the GMM over R. So total is 2 times, right? Of course, this is wrong. Okay. Why? Anyone made this mistake? Anyone times 2? Or all very smart, all got it correct? But are you curious, even if you got it correct, right? Are you curious why is it not 2 times? Why do you not need to times 2? Anyone want to offer your explanation? Why is it that we don't have to times 2? Have? Don't have? Nobody know? Okay, then I will just tell you the answer. You see, GPE, right, is always one interaction of GPE, right, arise from one instance of there is no meaning, right, to say what is the GPE of, you see, we are too used to it. We always say, what's the GPE of a rock? Okay. What's the GPE of a person, the object? But you got to realize, right, this GPE arises because you bring a rock from infinity to a point where Earth has gravitational field. Okay. And that gives rise to the GPE being manifested. Because that's exactly right, the definition of GPE. So it's because got interaction between two objects that carries mass. Then there is a GPE arises. We usually, right, attribute it to the attributed, right, to object. Okay. Not object now, but more of like the subject in question, okay, which is like the rock, man, or etc. But it's actually more correctly, right, to be attributed to the system, or is the rock Earth system got this GPE, Earth man system got that GPE, okay. That is why, right, this question is stated as GPE of the system, okay? Because you cannot say GPE of either star. It's not correct to say that. But not very correct. Okay. But do you need to worry about that much? No need. Oh, you can just do whatever you are doing for most situation. It's just this case, right? In case people think, oh, why no need to times 2? This is the reason. Because, right, there is only one GPE associated with one instance of gravitational interaction. Okay. Then calculate the total energy. You calculate the GPE from above already. Then you calculate the KE. And then you see here the KE need to times 2 because each of them have a certain KE ma. Oh, then you times 2. Then finally total energy, you add up these two values. So by the time people come to here, right, the correct answer, quite many people will get treated already. They will make mistake one way or another. Finally, right, this last part, wow, very difficult. This is, I feel, a killer. This is why I put it right as the last question of this paper. Good for you to think. So you see here, right, this we deal with the phi against R graph first, okay? You see the potential, right, anywhere along this line, okay, whether you're talking about here or here or here, you got to realize, right, that they are actually the sum of the individual potential, okay? So suppose, right, you have at this point, then you want to draw this line to here, so this is a particular R. You want to draw another line to here, seeing it. It's the same R. So what is the phi at this point, right? It's simply, right, 2 times of the individual one, okay? 2 times, I hope you understand what I'm saying. Okay. And hence, right, as you come nearer and nearer, although it's not linear, as in you're talking about the diagonal, but as long as you're coming nearer and nearer and nearer and nearer, right, inwards, the phi, right, will get more and more negative. So this part of the graph, right, will simply be like that. This part will also be the same. Okay. It's simply less and less, smaller and smaller in value. No, let me be clear. It is more and more negative, yeah, but smaller in value. Then finally, right, at here, what do you expect the phi to be? See, at here, right, the phi is just the sum of the two contribution again, no? So naturally, right, the contribution are finite. So the phi here, right, must be a value that's finite, okay, and it's the minimum. So you connect this part, it's just agar-agar. So this will be the graph, okay? So when it's very far, this part, right, will resemble one over R, okay? Same for the other side, but you'll resemble less when you come nearer. So as you're in the middle, then you have to make sense that this is a finite value. Okay. And once you have this, right, to get the next graph is not difficult anymore. Okay. Because you know the G is equals to minus the phi dr, okay? So this portion, right, is all negative gradient. So positive G. And this part is opposite, so this is negative G. And this is 0G. Which makes sense because, right, at point C, the two planets, the two stars will pull whatever is there, right, or opposite direction, or an equal pool. Thus, right, you expect your graph to have a few important point. This point will pass through 0. Okay. Then, right, you look at this gradient. This gradient, right, from here is like close to 0, steeper, steeper, steeper. Then because got a turning point, so the gradient, right, less steep, less steep, less steep. So if you say out, right, in terms of the value, okay, the gradient, right, is close to 0 here, or bigger, 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 then becomes smaller, smaller, smaller again. Then the same happens on the other side. Yeah, here the gradient are positive and increasing. So the G is negative and increasing. So bigger, 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 then smaller, smaller, smaller. Yeah. So connecting the dots, something like this. Okay. Do you need to get the shape until it's super accurate or not? Oh, no need. Roughly, right? How you see I draw, if you draw this full mark already. Okay. The suggested solution will show something that's slightly different, but this is full mark already. And how you know, right, that this is a curve? Okay. So all you know is the dot, right? Just now, as we deduced, how do you know I join them up, they will become a curve? Reason being, right, this is a very graduated process. There's no sudden point, right, whereby there's a change in something. Before this point is like that. After that point is the other way around. That kind of drastic differences in the circumstances. So we don't expect any sharp turning point. So the turning point will be a smooth one, which is why here is like that. Okay, which is why here is like that. Okay, so which is why it's a curve. It's not going to be a spike. Any question?
Can you explain what you mean by finite value?
Oh, finite value, which is you see, normally we expect, right, the value of phi to be like 1 over r curve, right? Or is a 1 over r. Then but here, right at the center is simply, you see, we use the symbols given, right? The phi at this point is simply equals to 2 times of the negative g m 1m, sorry, gm over the radius r upon 2. Yeah, it's simply a non-infinite, non-zero is a finite value, and it is the largest. Okay, it's the largest because the potential simply add up. Also, you are adding up 2 negative number at all time or at all points. Then which point, right, will have the greatest the greatest negative number, right? The most negative number, not the greatest, the most negative number is where the radius is the smallest. Not the radius, the separation is the smallest. So it's this point.
How come it's r over 2?
Oh, because it's what is defined in the question, right? The question is using, I'm referring this as r, okay, in case you are confused. So it's r over 2 long. I'm using the r as the separation. Okay, so at the center, right, the r that you substitute in will be r over 2.
Okay, thank you.
if right, I find the first graph, right, is actually manageable. Okay, so this is the first graph. If you have gotten the first graph right, and you stick to this rule, okay, don't veer off, don't think, don't go and use extra thinking, right? How to visualize such a gravitational pull. Don't visualize, you just use math and math your way out, right? So just ask yourself, how does a gradient vary and how will hence the GB, right? You will get this graph one, confirm one. So it is right, a very disciplined, sticking to the rule, okay? But right, is there meaning to it? Also have. Because right, you see, this question is telling you that the G, right, you see, what constitutes a G? It's like that, ma. At this point, someone is pulling, so the net G, right, is like here. Okay. Then you go nearer, right, at this point, this force is like even bigger. To sleep. This G is even bigger. This G is even bigger. And the net G is like here. Complete the parallelogram. But right, something else changed. By here, right, let me zoom this. By here, right, this G is super big, contributed by this guy is very big. This is contributed by this guy is very big. But then, right, you see, the component of G that's along the axis, right, is very small already. Because, right, the angle is very steep. We are talking about 2 times of the cosine of this vector. So which is why, right, as when you go from very far, nearer, the arrow, right, the individual arrow become larger. But you're also taking a smaller and smaller fraction of the component. So at one point, right, the growth of the length of the arrow outweighs the diminishing ratio, because it's a component, and over that point, right, the component grow longer, so the vector grow longer and longer, but the decrease due to the taking the component, right, become even more significant. So it outweighs it. So after that, right, G will start to fall. If you think about it qualitatively, right, that's how you understand. But it's too cheap already. That's why I say, right, if you math your way out, right, just using this equation, you can get G reliably. So I will advise, right, for a normal student, this is how you should do it. Do you understand what I'm saying? Okay. At this point, right, any feedback, like how you would like me to do things differently, or any suggestion for the future session? Or you find it's followable, good thus far?
Yeah, I think it's okay.
My voice made you feel like sleeping? Okay. So look out for the session 6. I think I want to complete that in one session. Although it's very ambitious, that one is 20 page. Okay. So you can try to do as many as you can. We see how because I still have more. I still have more coming up. So I'm not sure whether I want to do over 2 sessions or what. That one is definitely quite challenging. Okay. Not every question is challenging. Some are challenging and some are okay. The circular motion altogether got 3, increasing difficulty one in their order of appearance. Okay. Then I also have other, I think I still will do it in a mixed style. So it's across the topic. So it force, like each session by itself, right, will revise a bit of everything. Yeah, so I see you the next time. I don't know when to hold the next session. Sunday will be quite rushed, right? Maybe you can't do it on time. Any suggestion? On Monday, Tuesday. Tuesday is a good day for me because I have no lesson that day. I mean, I'm attending a full-time course, so my daytime 9 to 5 is occupied one, very packed. But next Tuesday happen to be free, so that's a possible day. Monday is also can. Monday then is after 5. Or you think about it, we can finalize in the WhatsApp group chat. So I need to go and cook already. So that's all for today. Have any question, you WhatsApp me later. Okay, bye-bye.
Thank you, Mr. Quek.
Mr. Quek.
Thank you for coming.
Mr. Quek.